Um, Initially, we're just going to do an intro and some basic scripting into using eBPF. How would you go about doing that without needing to write a lot of code? And what's the fastest way to get you up and running? Once we've covered that, we'll be going into some slightly more complicated application development, but hopefully not too bad to scare you off. And then lastly, we'll be writing a very simple firewall that is run entirely using eBPF, and go into the reasons why you'd want to do that. So in terms of a little bit more detail into what we'll be doing in section 1, we're going to introduce you to the world of eBPF, understand where it fits into the larger context of the Linux kernel, understanding what probes are, what hooks are, where you find them, what you do with them, and then finally getting started writing your own one-liners, or initially just hooking into the ones that we provide you with. So section 2, we're going to dive a little bit deeper, and we're going to write actual scripts for an eBPF program, as well as slightly longer BPF3 scripts. Don't worry if this doesn't make sense right now. Hopefully by the time you hit this section, things will start understanding a little bit better. And then lastly, we'll be talking about user space to kernel space signaling. And this is important because if you want to control your eBPF application, the eBPF application actually runs directly in the kernel. So you need some way of talking to the kernel without writing a kernel module. And then lastly, probably the shortest bit of the track for the day, but hopefully just as interesting, we'll be talking about writing your own eBPF firewall, why you want to do that, and how you go about doing that using the XDP framework. So first of all, this course is hopefully there to make eBPF work for you. I don't know what problems you may encounter on a day-to-day basis. I don't unfortunately work in the analyst pen test space on a day-to-day basis, so I don't know what issues you may or may not have. I don't know what issues you may also have in terms of doing performance analysis or debugging within your operating system. And I think knowing your operating system is just as key, because very often people treat the operating system as a black box of sorts. We use it to do stuff, but we don't really know why it's doing what it's doing. And when something goes wrong, very often it's easier to Google for an answer, but hopefully we'll be getting around that today. So please ask questions, propose suggestions. If you think something I'm saying is wrong, please point it out. I really don't mind. So Simon is going to be helping out with questions and answers where possible in terms of aggregating them, since I'm not looking at the chat directly all the time. But if you do want to, please feel free to unmute yourself and just ask questions if that's going to be easier. So before we actually dive into eBPF and get into deep into the topic, these are just some interesting things that people have done currently with eBPF that I thought folks may find interesting. So the top one here is the theremin that Brendan Craig, who is one of the leaders in the space, built using eBPF, and I'll just show a very quick video of that that he presented at AWS Invent. And what this is doing is it's intercepting his signal from his Wi-Fi connection to his phone and printing out the signal strength in bars, and then you probably can't hear it, but it's playing a audio sound as well. Now to do something like that, where you access the kernel Wi-Fi drivers and did something with that information, would have previously required a kernel module, or at least some very low-level C interactions, or even possibly assembly interactions with the kernel itself. And for the most part, that's out of the reach of most folks. Like, nobody's going to spend time writing a kernel module to make a small game that works on your Wi-Fi signal. Obviously, there's a bunch of other cool things you can do with it, So for example, the person behind the DevOps Spiral article uses eBPF, or at least his Bluetooth driver, to detect when his phone is near to his PC, and uses that to unlock and lock his PC. And then one of the examples that I came across as well was overwriting syscall return values to great effect. So for example, you could return the syscall that returns what your current user ID is. So you could use that to trick applications to thinking that you're someone else. Now, obviously, there are ways of doing all these tasks using existing applications or existing kernel modules, but they tend to be fragile and not very portable when you think about it. And then lastly is BPF Inc. from booking.com, which again is more along the lines of an auditing environment. So for example, you can ask it to keep track of a number of files or directories, and it will monitor them for changes and keep track of who changed it, what changed, and all in a configurable environment. It uses the hooks into the kernel syscall, so whenever a file is changed, you have to go via syscall, and it uses that to keep track of what is changing. Cool, so what is eBPF? And I'll be shortening this just to BPF going forward, so effectively they should mean the same thing. As the definition that I pulled out from the reference guide says, it's a highly flexible and efficient virtual machine in the Linux kernel, allowing you to execute bytecode at various hook points in a safe manner. And I think the very important thing here is the fact that it's being done in a safe manner. So a kernel module, if you had to run some custom code in your kernel to do whatever you want it to do, if that crashes, it takes down your entire operating system. A BPF program that, as you will see a little bit later, is meant to never crash, and if it crashes, it will never affect the kernel itself. So it gives you a very fast, efficient, and safe way to execute code in the kernel in a way that you can reliably run in production. So for example, you don't want to go to a machine that's experiencing problems, load some code up, and then cause even more problems to the environment. So again, just for so folks that may not have encountered it before, the actual acronym BPF stands for Berkeley Packet Filter. It's also at this point in time referred to as the classic BPF, and then there's eBPF, which stands for Extended Berkeley Packet Filter. That's a bit of a misnomer though, because it doesn't technically stand for Extended Berkeley Packet Filter. It's just the new name that's given to the technology because of how different BPF or classic BPF is compared to eBPF. It can be thought of in the same way as Docker versus containers. Docker is what everybody knows when they talk about containers, but the underlying system is usually done via LXC or whatever other container system you want to use. So you probably have been using the classic Berkeley packet filters for ages now, and you probably just never knew about it. It was introduced in roughly 1992 to the TCP dump application to be able to do packet filtering very efficiently. And if you ever want to see this code on your own machine, if you just add the -d parameter to your TCP dump filter, it will print out the BPF assembly code for you to view. Honestly though, this is fairly pointless because there is, unless you debugging the BPF JIT or the BPF verifier, you're unlikely to be able to use this in any efficient or intelligible way. You could copy it between machines and it may work, but honestly there's probably easier ways to accomplish the same task. So this is the assembly bytecode that gets executed by the virtual machine we mentioned earlier, and it's what's used to filter packets for TCP dump. Now jumping in a little bit deeper into the larger ecosystem of eBPF, or as I mentioned, just BPF going forward, the workflow is fairly simple. You submit BPF instructions to the verifier. So this would be submitted as a complete application. the verifier checks that everything is okay, and assuming it's okay, it will go to the JIT compiler, which compiles it for the machine it's running on. There are ways to bypass this and use the interpreter, but most kernels will disable this by default, so you're unlikely to use this. So once the JIT compiler compiles the code, it will get added to the kernel in the form of machine code, which is why it is so fast. And at this point, the machine code or the BPF program has access to a number of things. It's got access to 11 registers of its own, which again doesn't really make that much sense now, but it may make sense a little bit later. But all this means is it can do certain operations extremely fast, and it will store the results of some of those executions in one of these registers. At the same time, the machine code can talk to the rest of the kernel using certain BPF helper functions. We'll cover some of them, but honestly, it's a growing list, so we can't ever cover everything there. And then the last two functions are the BPF context and the map storage. Because you're executing code in the kernel, you technically don't have access to any memory space to execute your code, to store data while your code is running. Instead, you need to be using the map storage, which is a virtual file system that the kernel will write to whenever it needs to store data. Now this is used for both data storage as well as communications between the kernel space and user space. It's how you do signaling between BPF applications and any normal user application that you would be writing. The BPF context is very dependent on the environment, as the word kind of says. It's context sensitive information that you can use to get more information out of your program. So for example, if you think about the context in a network filter, it would have access to the packet. But if you think about it in the context of a system call, you'd get access maybe to the system call ID or any other parameters that were sent to that system call. So with the basics of how BPF works on a higher level, just a short history in terms of how we got here. So as mentioned, with classic BPF, it's been around for a long time, but eBPF has only been around since, the eBPF that we use currently has only been available since kernel version 4.8, which is roughly around 2016. So if the machine is running an older kernel, chances are you can't use that without loading a kernel module or loading an updated kernel. So eBPF, as I mentioned, it's been around for a little bit longer before kernel version 4.8, but it wasn't accessible via system call or any other means at that point. So you needed to have been writing internal kernel code to be able to access that. And then just some points that are worth bearing ahead of time. This talk won't focus too much on the security aspect of eBPF or BPF. There's other folks that have done a better job at that, specifically the NCC group. These links should be on the machines that you have access to. Otherwise, if you need any of the links, please ask me and I'll post them to the chat, or you can get them from the slides later on. So much of the content around eBPF in terms of talks and papers and blogs will be coming from a person by the name of Brendan Craig. He is exceptionally foundational in terms of getting information out there, getting people to understand how it works. He's actually written the book on eBPF, which came out sometime last year, and is probably one of the leading people out there pushing the art of BPF. And he does this because he works as a performance engineer at Netflix, and because of the efficiency that BPF provides you, it makes his life much easier. Finally, just like any other application out there, eBPF is not invulnerable to any sort of exploits. The ZDI blog listed here, as well as some of the other research that has been done, shows how researchers out there have found bugs in the verifier and the JIT environment. Now, that doesn't affect the actual code you write. It affects rather the verifier that verifies your code, So the exploit doesn't affect runtime of the code, rather it's just a way to escalate privilege within the kernel. And it's just another tech factor like any of the others out there. So existing tooling that uses eBPF, there's a lot out there already and the market is growing. These are probably the bigger names in terms of products that are using it. The first one, Cilium, is probably one of the bigger companies that are actually building products around eBPF. Now, keep in mind when we talk about products using eBPF, they use it in a way to do deep level signaling within the kernel to make decisions for the application that they're providing. So in the case of Cilium, they provide a Kubernetes networking and policy proxy service. So what that means is you can specify on an HTTP request, you want to allow access to a post request, for example, only from internal containers. So when data comes into the Kubernetes cluster, it will check, at a networking layer, does this need to go to our proxy or not, if it's internal or external. If it's internal, send it to the proxy to go check if it has permissions to access the GET or POST request, for example. Otherwise, just block it entirely. After that, NetData and Prometheus, BPF exporter, as well as the Netflix vector application, all provide metrics from your system in a visual way. So NetData already provided a bunch of metrics. They're now just using BPF to do it much faster and more efficiently. So the CPU usage for getting those stats becomes a lot lower. NetData and Netflix Vector are on-host solutions, and they are a lot more efficient in terms of it's one package provides you with everything, versus the Prometheus BPF exporter. They would collect your BPF metrics and ship it off somewhere else, or rather get it viewed somewhere else, typically in something like Grafana or any other graph environment that you may be using. Next is Sysdig. They use BPF to do security compliance and monitoring of environments. They do this with the use of a tool called Falco, which allows you to do behavioral security using BPF hooks. So for example, if you wanted to monitor the number of exec calls that are happening on the system, Falco would keep track of that, and if it spiked up, you could set up an alert on that. Tracy and OS Query rather, are just tools that can query the BPF environment, and they provide a way to do tracing across containers and your current system. Tracy is aimed more at the container environment, while OS Query is meant more at the host system, but they both allow you to query BPF metrics in an interesting way. So before we even dive any further in terms of where to hook BPF applications into your kernel, it's worth understanding that you need to know where to plug in these applications, because BPF applications by their nature don't run on their own. So it's not like you run a Python script and the script does whatever it needs to do. BPF applications have to attach to a hook, and knowing where to hook is half the problem. So the use method by Brendan Gregg talks about understanding the utilization, saturation, and errors in a system. And when you look at that method, so let me just find the right link here, he's broken it down very nicely in terms of the different environments and what metrics you would want to look at. So for example, if you're having issues with your CPU, you may want to look at the perf command and what hooks it's using versus memory capacity. Where would you want to trace the environment there? So you probably want to look at mallocs. On the network controller, there's other information you can pull out from netdev that would give you a greater understanding of what's happening on your network controller. I'm not going to cover every single one of these interfaces. It just happens that if, for example, you wanted to monitor something to do with the CPU, it's useful to come here and understand which areas of the system you would want to monitor saturation, or monitor for errors, or monitor for general utilization. So it helps you narrow down what part of the Linux kernel you want to monitor. Then, as often is said by many a hacker, look at the source. The BPF header files that are provided as part of the Linux source have a ton of information provided in them. And specifically the Linux bpf.h header file, you don't need to understand what we're pointing out here, but all the enums that you would ever see listed in any of the programs, as well as comments explaining what they do, when they should be used, the functions that are available to you are all listed here. So for example, these are the only functions that can be used within a BPF application, i.e. anything that starts with BPF underscore. So for example here, BPF underscore SKB store bytes. They've got a great description of how it's used, what's the return value, what's the parameters that you would pass to the function as well. So that's just an easy way to get a deeper understanding if you needed to call a function and you can't find any documentation on that. Because unfortunately there isn't a great source of documentation aside from the source code at times when it comes to BPF related information. The Cilium docs are a general great place to be looking at when you want to understand BPF and XDP. So this is meant both as a quick reference guide as well as a very deep understanding. So if you look at all the information here, they've got examples, they've got code flows, they've got examples of how to debug these applications. Like they've got mostly relevant information. It's not always the most up to date, but it is fairly recent. Let me just check. Maybe I've got the wrong version. Sorry. But you can find a significant amount of information here before needing to look anywhere else. So even before you jumped into the kernel headers, it's sometimes better just to look at the Cilium documentation because, like I mentioned earlier, they are probably one of the biggest development teams using eBPF at the moment, simply because they're using it for Cilium, which does the networking layer for Kubernetes. So this is stolen very graciously from the Cilium docs, and it just kind of shows you on a high level where you can instrument things in the kernel using eBPF. So keep in mind as well that while you can instrument functions in the kernel, you can also instrument function calls and other hooks that are not in the kernel but are in user space. So for example, a process that has send and receive messages, anywhere where you see this BPF icon, you can set up a hook there. So for example, you want to hook anytime a specific syscall happens, set up a BPF application that responds to that syscall or any syscall in general. Want to monitor the virtual file system, there's a hook for that. Want to monitor low-level disk usage, there's a hook for that. Just about every part of the Linux kernel, from the user space down to hardware layer, the hardware level can be hooked into, and that's sort of how the original demo that I showed with Brendan Craig making that Thurman on YouTube, where he moves his phone closer and further away. It's based on hooking the network, his Wi-Fi cards debug information. Obviously you don't need to go to that level, but if you feel that there's something you need to debug there, or you need to trace, or you care about, then you know you can do it. So to make life a little bit easier, since BPF has been around for a while now, you don't need to start off from scratch writing your own scripts everywhere. The community on a whole has provided a significant number of scripts that you can use to monitor just about every part of the kernel here. So as an example, if you wanted to look at system libraries, you could use the syscount or killsnoop or execsnoop. If you wanted to look at the system call interface, you could use TCP live to inspect the TCP UDP stack. You could use trace or ext4 distribution to check the file system. And there's a number of scripts that are basically out there already for you ready to use based in BPF that you can just execute, and it's where we'll start this learning process basically. So you'll get used to using some of these basic scripts, see the results, understand how they work, and then break them down and then start using them on their own. So each of those areas that I pointed to here previously, what exactly are they monitoring? So it was sort of alluded to with the Cilium documentation, but we hook into probes throughout the kernel. And these probes are typically referred to as K probes, since that's the vast majority of things that you care about that you can't monitor in user space. So we monitor kernel probes, as well as trace points, as well as user probes and user-defined probes. So there is a good few different locations that you can use to monitor. If you ever wanted to find out what probes are available for you to check, you can cat out the /proc all sims file on your local machine, and that will show you what you could hook into if you wanted to. It's not the most concise way to do it, and we'll demo a different tool that allows you to search for specific hooks that you can use while testing. Now, it's worth going through, if you get the time a little bit later, is understanding how K-probes work and why they were used for debugging previously, before they were used for eBPF, and how they fit into the life cycle of things. So we're just going to give a very short breakdown of how they work. So they were meant as debugging mechanisms. So when they were originally inserted into the kernel, you would use a K-probe to put a debug point so that you could step through kernel source code. Now that was done originally using the int3 instruction, but with current operating systems where optimizations are enabled, we don't need to use the int3 debug call. We can rather just, the kernel rather, once it's generated the BPF assembly, it just inserts a jump instruction to jump to your current bytecode, at which point it will run through the usual process. So we won't be setting up single step handlers, but it will effectively execute your piece of code and then go back to the original instruction before your code was called. So very quickly though, when we talk about BPF, it's the bytecode in the assembly level language. But as mentioned earlier, it's almost impossible to write useful applications at the BPF assembly level. The instructions and the way it's written is just too arbitrary to be able to put together anything useful. So instead, there's a number of tools such as the LLVM compiler with the BCC toolkit that you use to write higher level languages that will compile down to the BPF assembly language, which will then get compiled down to the bytecode that gets added to the kernel. So typically you'd be using either BPF trace or kubectl trace. Trace and BPF trace are useful for writing one-liners, but as you'll see, they also allow you to write fairly decent scripts. LLVM plus C, and I should have included Python and any other language that you want to use, also provide a similar functionality, but now get down to a deeper level where you want to automate things a little bit more. kubectl trace is very similar to BPF trace and the trace command. The only difference being that it allows you to run your BPF commands across an entire cluster. So for example, you wanted to trace why the CPU usage is significantly higher across a number of probes. You run kubectl trace, it will execute the BPF trace commands on each of the nodes or pods rather, get that information, collect it, and send it back to you. So the BPF trace and kubectl trace are examples of front ends, while BPF is the actual language. LLVM and BCC are front ends, but they're more of a programming front end than an actual application. Sorry, 1 second. So there's a number of reference guides that you should be looking at, and they will be available in the links that we provided you. But I may as well just post it in. Thanks, Leon already posted it in the channel. But the reference guide is probably your go-to location if you aren't using the Cilium documentation when it comes to anything BCC or BPF trace related. The reason why is that documentation here is actually fairly concise. They have a great number of examples, and it's always up to date because it's part of their Git repository. So anytime something new gets added, they'll update it there first before updating blogs, for example. The other great thing is because the GitHub location is all just a Git repository, they've got a significant amount of examples that they've included. So from the root of the repository, if you look at the examples folder, they've got in almost all the common languages examples of how you would go about using BPF using the BCC toolkit. Keep in mind this is specific to the BCC toolkit, so it's not always applicable if you write your own code, which I'm assuming you'll probably never do on the assembly level. Now again, if you get time and if you really want definitely a better job than I can do here, understanding of both BPF and tracing as well as instrumenting your Linux environment, the two books by Brendan Craig, and there's another author whose name I can't remember now. These are the only two current books, so they came out towards the end of 2019, so they're still very relevant, is the BPF Performance Tools and Linux Observability with BPF. Both of them have great examples, cover all the different environments that you would care about that we may not be able to get into today, for example. So if you get a chance, I haven't seen them go on sale yet, but they're great books and worth investing in if this is something that you end up doing fairly often. So I'm just going to let you ponder over this example for a Hello World application. It should make absolutely no sense to you right now, but it's just a primer for you to get yourself ready for what you're going to be working with going forward. And we'll get back to it shortly. I just want to get some water very quickly. Alright, so this is a BPF application written using the BCC toolkit, written in Python. And we'll get back to this later, but it's just so that you can kind of see how small the applications are in context. It's obviously not as simple as a Python Hello World application, but it's still fairly concise in the grander scheme of things. So stepping back a little bit now, you saw the code that you're going to be writing a little bit later, but let's not get ahead of ourselves. In the end, the more you can do with a one-liner, for example, it means it's going to be in your history, it's going to be easier to share. You can generally get away with writing 90% of your queries against the Linux environment using some of these one-liners. Now, at this point, I hope that everybody that's in this workshop has gotten access to their Linux VM, and all these tools are currently set up and installed for you. Now, to install them on your own operating system, it really varies. You can install it from the BCC toolkit. They have an install instruction, but it's actually fairly involved. So you need to clone the source and then compile it locally. That can be quite involved. So there are packages for Ubuntu as well as other operating systems, but we can't cover every operating system here. So we will mostly be looking at Ubuntu in our examples. Typically, the tools are installed into one of two locations, so user share BCC tools on your local machine, or user sbin and then the tool's name -bpfc. The second format is more popular with Ubuntu. So I haven't seen that on Arch Linux, for example, who installs it everything in the user share location. It does mean that anytime you need to look up an application, you need to make sure you're using the one that ends with -BPFC C. Otherwise, you're using some other application, and it does make finding the correct application a bit easier. So, example, if you wanted to run exec snoop on Ubuntu, it would be exec snoop -BPF CC. Cool. So one-liners are the best thing. It's probably one of the things that got me started with PowerShell and many other languages. I'm just going to paste this cheat sheet into the console, and that will hopefully make life a little bit easier when you're writing some of these one-liners. As you can see, they're fairly short, but they use a lot of acronyms. So understanding what T stands for, what U stands for, what each of the variable types are, what's available, all of that is effectively on a 2-page document. So it's always good to have this on hand when you writing something new. So just to get started with things, if you haven't already, connect to your VM, and we're going to run the exec. Now I can't select stuff. And we are going to run the command that's listed here. I'll paste this in the command line, in the text chat. And what this does is it traces all new processes that are running. So you want to be using this in a tmux session preferably, because while the BPF trace is running, it obviously blocks stuff, so you can't do anything else while it's running. So spin up a tmux session. Let me do that as an example. You will also need to run everything as sudo because BPF itself requires elevated permissions, since unless the user that is executing it has been given the correct permissions. By default in Ubuntu and most operating systems, that isn't the case, and honestly it can end up causing you more problems if you try and enable it. So it's honestly just easier to test that using the sudo command. So I'm just going to paste this as is. You'll see it says attaching one probe, and nothing really happens at that point, right? But if we hit Control B to create a new terminal and we come back, you'll see a bunch of things happen. And what actually happened here is we captured the exec VE command and all the parameters that were sent to it, and it's been printing it out for us now. So you can see, I don't know what's Bumblebee doing on my machine, but it's obviously doing something with syslog. When I created a new terminal, my directory was listed, uname was run, my ID was printed, and a bunch of stuff are going to keep on getting printed for as long as I keep this running. Hit Control C to end that, and that's your first BPF one-liner. I'm just going to pause for a second here, and if anyone has any questions before we go forward, or any issues connecting and running a command, let's get that sorted out first.
I have a dumb question, Jamil.
Sure.
I'm looking at the one-liner and I'm looking at the cheat sheet.
Yes.
And I'm not sure how to glue together the...
Right. Sorry, that's just, we're just priming you ahead of time. I'll explain on the next slide how everything comes together.
Okay.
So that was just for you to see some examples, make sure everything works, make sure you can connect to your environment, make sure that everything you'll need going forward is available for you.
Okay.
But cool. I guess if there's no other issues, may as well continue. And let's go back into this interview.
Sorry.
Sure.
The first point, how much is connected in SSH?
Sorry, can you
I mean,
just...
username or
Oh, so the username is Ubuntu. So it's just you'll get a key from Simon. So it's SSH with that key Ubuntu at whatever the IP address they gave you was. You just need to ping Simon. So I don't know why
that works.
he...
Ubuntu do what?
Sorry, can you just say that again?
Uh, sorry, I said that works now. I will check with them, the user Ubuntu, so it's okay.
Okay, cool.
Thanks.
Cool. So, Ove, I hope I'm saying your name correctly. I've just pasted his handle there. Send him a DM, and he'll set you up with everything you need. If we run out of VMs that are available, we can spin up more if there's more folks that need access, because I don't actually know how many are available on this channel actively. Okay, so let's break down this command that we just had a look at now. So we ran the BPF trace execve command. So obviously the BPF trace command is the actual application. -e executes a script in line, so anything that you provide in text, in quotes rather, is what's going to get executed. You can provide a text file if you want to do more complicated scripts, but this is just focusing on the one-liner. Then the next bit is the most important bit. From the first quote till the first space, which I hope you can see after the word execve, is the actual hook into the kernel that we want to monitor. So there's a number of what you call it, hooks that you can use, as mentioned by as mentioned previously. Trace points are one of them, but you could also hook into a user probe, which is in the user space, a kernel probe, which is in the kernel, and a USDT, which is a user defined, so basically a custom user hook. And in this case here, we're looking specifically at the trace point. It's very similar to a kernel probe, but it's more for tracing, so you don't get as much information out. Then we're looking at the syscalls, let's call it group. So each of these things are separated by a colon, and that defines a group. So trace point, colon, syscalls means we're now filtering down to the syscalls level, and then colon again, what specific syscall do we want to trace? And in this case, it's sys enter execve. Once you've got your probe defined, here, within the curly braces, you write what you want to actually execute. So in this case, we're joining the argv parameter, which in the case of execve is all the parameters that you want to use to execute your program. Now, the obvious question at this point is, what can I trace? Right? There's so many things, and getting out that file is just impossible. You're going to look at pages and pages of it. So if we get proc alt sims, as you can see, like it's a lot of information and probably too much, and trying to determine exactly which ones here are trace points versus debug points can sometimes take too much time. So what we do instead is we use the BPF trace-L parameter, and we use globbing to find what we want. So in my case, I just want to find what sleep functions are available. So if I do -L, if you just put sleep without any globs, you'll see that there's nothing returned, because there is obviously no trace point or user probe or kernel probe that matches the word sleep. But if I glob with the word letter star before and after, you can see it's found a number of probes now. So it's found K probes that have the word sleep in it. If we go up, you'll see it's also found trace points that have the word sleep in it, and you can see the different groups that are available here. So for example, in the trace point section, we have VM scans, which are related to your virtual environment, syscalls, schedulers. There's a number of internal system trace points that get exposed. You probably won't need all of them. The most likely place to look is for the trace point colon syscalls, as that's typically what your environment is invoking from user space. Now, if you look at this, there's a lot of sleep syscalls, and unfortunately, there isn't a easy way to know which one. And you'll also see they duplicated. So there's a sys enter clock nanosleep, and there's a sys exit clock nanosleep. I will go into this a little bit later, but just to clear up any confusion ahead of time, enter is obviously when you're entering the syscall, and exit is obviously when you're exiting the syscall. So you need to hook at a specific point to be able to do different pieces of functionality. Now you can trace, for example, as we mentioned, just everything in general, but if you wanted to find out what probes are in a specific application, which is useful when you're debugging a specific application, say you're looking at a database or a web server or whatever it is, you can use our second example here with the U probe. Now the U probe is going to be obviously things in the user space, and most applications are compiled and run in user space, not in kernel space. So if we run BPF trace and then we provide, I don't know if I can copy that prints out all the user probes that are available within the bin bash binary. Now you can do that for any binary, and you'll be able to get a dump of everything that's available in there. And I don't know exactly what we would want to read from the bash binary itself, but maybe you want to find out whenever bash is doing a free and a malloc, right? So for example, if you have a number of allocations of memory but no frees, there's a chance that you have a memory leak, for example, and that's one of the examples of things you can do. So keep track of the number of allocations, keep track of the number of frees, let it run over time, and if they don't match, you know something's going on with your application. But as you can see, it actually covers a significant amount of things that you can monitor within the application. That's like 10 pages just from one binary alone. So if the BPF trace-L with a globbing doesn't give you something, and you know it's a application that you have access to, try the U probe or just U, for example, which you can see in the user trace here. U probe is returned as just the letter U. So running that on any application will obviously give you a dump of whatever is available there. Now, in this example as well, let me just check my next slide here. We've got this join and then args and argv, right? But how do you know what parameters are available for each of your function calls? To do that, you use the -v parameter and you provide a probe that you want to query. So if we look at zread here, okay, so you need to actually provide a kernel trace, not a just give me 1 second. So if we look at nanosleep, so that's the trace point in the kernel, and obviously what attributes are available. Now I don't actually know what RQTP means or RMTP means, but it's probably something to do with the timer, how long it needs to run, or how long it has run at this point. But that's up to you to now possibly go and check in the kernel itself and see what parameters it's using, and then use that to your benefit. You'll typically also always get a syscall number if you're tracing a syscall. That's just used if you ever want to group your data by syscall. So one of the examples later that we'll show is you want to find out what syscalls a application is running. It's easy to group it by number and then figure the name out later. Cool. So we're going to, I guess we just covered this now. We're tracing the trace point, We can trace kernel probes or user probes. And yeah, we've just traced syscall. So I jumped a little bit ahead there, and I showed how to dump the parameters for our call. So in this case, if you had to do a BPF trace -LV on the sysenter open, that's the open C binary C call to open a file. And as you can see, you need to specify the file name, the flags, and the mode for when you want to open a file. So all of those are available to get printed or counted when you are using the BPF trace application. So before we jump into a few more examples, if there's any questions, please raise them now. I just need to take a sip of water. Not used to so much talking. Right, so continuing on. Yeah, as Leon just pointed out, there's 43,000 BPF trace locations if you just do a word count on the number of lines that are printed. So you can touch just about every part of your kernel. And a good example of things that you may not be aware of is things like your Wi-Fi drivers, things like your Bluetooth drivers, things that may be exposing information but are not being logged anyway. So you can hook into that even though it's not being logged anyway. So back into our examples here. And we are now going to do syscalls by PID. So this is a good example of showing a lot of things happening at one time. So I'm going to copy that out and run that in the console, and we'll discuss that as it goes. So as usual, because we've only specified the sysenter syscall, sysenter is typically run before any syscall itself. It's the lowest level syscall. It's running in the background, but as you can see within our curly braces, let me see if we can just zoom in here. I can't zoom in, sorry about that. There's no printing happening. We're not doing any joining or anything with strings, so there's nothing actually to show on the output of our console. It just says attaching one probe, and we kind of need to assume that it's actually doing something. So if I hit Control C to stop the probe now, you'll see it basically dumps all that information that we were collecting previously to the console. And what it means right now is it's showing the number of syscalls that each of my applications did. So for example, Chrome has done 38,000 syscalls since I started it, and I have no idea what they were doing, but they probably do a lot of stuff because they do audio, video, rendering, and all of that. So we'll show you in another example shortly how you would go about finding what syscall each application is running as an example. But for now, this just shows you an example of using maps, which we'll talk about a little bit later, and then grouping data by the application's PID and the application's name. You don't need to group by name and PID. It's just a little bit easier. So for example, you needed to kill something. You don't want to kill it by name. You kill it by PID. So this way we can see it. My audio is obviously doing something because I'm playing audio back and I'm listening to audio, so recording audio, but we don't know exactly what it's doing. We can't kill it for obvious reasons because we don't know what the PID is. So if we put the PID back in here, but once we Control C, we obviously don't know what the PID is mapping to, and without doing a lot of time wasting grabbing, it's easier just to combine them as one so that you can see both PID and the application name. Cool. I'm not going to exit that. So we talked about very quickly just counting syscalls. So that's stuff that's happening in your system. You finding out why your system is possibly so busy. But let's look at something on disk, right? So this syscall here is tracing again the open file calls. And this time we've got the string command and we've got the args file name. So we got the file name parameter from previously running this command with the -lv that showed us what parameters were available. And now we're just using, because printf requires a string, we're just converting this pointer to a string so that it can be read and printed out. So if we run this now, unlike the previous collector, it's actually got information that it can print and dump in real time. Now, I have no idea what journal D is logging so hard for, but it obviously figures that it needs to be logging something. But you can see tail scale is also hitting my net proc file virtual file system, and same for system D for the C groups. Now, in this example, we've obviously done a few more extra things. We've used another function that we've never used before. We've got this com parameter that we've used before, but we haven't really explained, as well as the string args file name. Now, if we go back to our cheat sheet, I'm hoping it's on here, you'll see com is a built-in variable name that basically is the name or the process or command name that's being run. So in this case, com is the process journal D or tail scale D, or whatever it is that you are tracing. Sorry. And then the strargs file name is just the file name out of the open syscall. So that allows us to figure out who's writing to the disk. And later on, we'll show you how to filter that so that, for example, we don't want to see all this journal stuff. We just wanted to see the tail scale, what is it writing to disk. Not that people often have to deal with this in a Linux environment, but if you wanted to find out what a unknown malicious binary is doing on disk, you could use this to go and say, filter all the open syscalls for this binary and see what it's trying to write or read on the file system. So as mentioned before, we're using maps, and maps are the only way to actually store data. And I just wanted to explain that a little bit more, because this is possibly the easiest way to understand maps, or at least this point in time. The map is anything with the @ symbol and then square braces. So that's the definition of a map. And then you can specify any number of arguments or error keys in this square bracket. So you could have com args ID is the syscall number, and you could have any other things that you wanted. You could have, I can't think of a good example for syscalls, but you could have multiple layers here. So you could have 3 or 4 arguments, and it would basically group your count by as many parameters you passed in there. And defining a map is fairly simple. It's a key value store. So whatever's in the @ square brackets is your key, and then whatever's on the other side is your value. The count function is simply a plus equals to or create value. So if there's no value for com args ID 1, it will set the value to 0 or increment it however many times we need to. So if we run this from the command line and let it run for a few seconds, you'll see now we have a little bit of a better understanding. We're not printing out the PID, but we can see that Chrome is executing the syscall 202 5,000 times. So now if we had to, because I don't know syscalls off the top of my head, if we Google for the syscall, we can look that up and get a better understanding. So it's doing something with futexes, which if I remember correctly are like mutexes. So it's using that for locking probably, and then 47 is receive message. So you can see, I don't know, libOBS is doing some network communications with the graphics driver most likely, and you can now get a better understanding of what each of these applications are doing on a deeper level. Now unfortunately there isn't a simple way, like I mentioned, to get a syscall number to name lookup. You need to look it up on something like this website, or you need to go and check the Linux kernel source for that. So if you open this, nope, I guess that links are a little bit old, but if you grab within the Linux source, they do have the syscall numbers available within there. So we've done general system monitoring, we've done disk monitoring, so now we're going to have a look at an example of filtering data on the network. And this example is going to be hopefully something that you can reasonably grok just by looking at. So we're changing things up slightly, but it's mostly the same. We're starting off with the KR probe, and if we looked at this cheat sheet here, KR talks about a kernel return probe. So we basically only care about the return executions for this syscall, for the socket send and the socket receive. And the reason for that obviously is because we've now got this / bit of text, and what the forward slashes do is indicate filtering. So anything within the forward slashes will act as a filter for your BPF trace command. So only if return val is greater than 0 will the values within our curly braces get updated. And talking about this in a whole, what this is trying to accomplish is collecting data once we've processed it in the send message and receive message. Return value indicates that we've accumulated a number of bytes, and then it's summing that up per PID, per application name, and then per return value. Now it's a bit apt to store the return value, and we don't need that, but it's basically summing it up per return value. So in case you have different packet lengths, you would have that printed out. So if we drop this into the console, you can see what this looks like. So the other thing, as I mentioned, is we've now got a comma in our probe. This allows us to match multiple probes without the need to use globbing. So for example, if we had to do sock_star, we may match too many network syscalls. So rather we just specify we only care about send message and receive message, and that lets us accumulate data in a way that we understand. So in this case, we got the applet pi. I have no idea what it's doing, but one of my network applets at the top is sending a whole bunch of bytes in and out. You can see Tailscale is also communicating with the network. Electron is probably one of our communication applications, and basically you now have a sum of bytes. It's either bytes or packet length, I can never remember, summed up per PID application and return value. Now again, like I mentioned earlier, you don't need to specify the return value since it's always going to be positive at this point. So you can group it just by PID and application name, and there we can see now what the totals for those applications are. Keep in mind this is both sockets as well as network traffic, so you may see things that are just talking to each other over the D bus, for example. Looking back here, right, so whatever's between the slashes, as I mentioned, just needs to be truthy. So is the current value greater than 0? If you had to specify return value is not equal to null, that kind of thing, you can't actually do nulls, but I guess not equal to 0 would also filter correctly. You can, anything that's available within this bracket should be available for filter as well. A good example, as I was mentioning earlier, is if you wanted to do filtering for applications that are logging too much information. So let's only filter syscalls for OBS. So we could do com equals OBS. I really hope that works. Let that run for a bit and hit stop. And now you can see just for OBS what are the syscalls it's executing. And I have no idea what each of these syscalls are, but you can see obviously it's doing 202 quite a bit, which means it needs to keep locks on something for whatever reason. but this gives you an idea of what an application is doing without needing to look at the source code at all. And as mentioned earlier, I think so, the kernel return probes allow us to access the return value, which is again one of the built-in variables listed on this cheat sheet. If you didn't use a kernel return probe, so if you just did send message, you can't use that exactly, but there is a send message hook that you can use for entry. It's fairly pointless because at that point you don't know if you've successfully processed the message or not. Cool. So we trace the disk, we trace the network. It would be nice to get specific, as we sort of described earlier with the bash example. It would be nice to go ahead and trace kernel user libraries. So any application that is using this library would get logged, and it's useful in debugging when you don't know how often something is using a library that you want to replace, for example. This also takes things to a next logical step, which is the interval S1. So now we have our one-liners getting slightly more and more complex. So we're doing our first probe, we're executing some code on it, and we're doing another probe, but we're executing different code on it. This interval S1 is just a probe as normal. So if we did BPF trace -L, and then we filtered for interval, it's in this list somewhere. We would find, or yes, we don't see it in here, but it's one of the available probes that you can attach to, and it's got a number of groups that you can use aside from second. I don't know if they actually list it on the cheat sheet. There we go. It's just a built-in timed reporting that you can use. So for example, in this case, we want to trace the libthread library, but we only want to do it for 1 second. So instead of manually hitting the Control-C at that point, which you could do, but it doesn't keep things very consistent, because how do you know you're waiting for exactly 1 second? Now keep in mind, this is going to fail because it's meant for Ubuntu, and Ubuntu stores its libraries in a different location. So if I run this, you'll see your first example of a failed attachment, and it's just telling us that it can't find that file. If I correct this now, as you can see, we have a glob in there as well. So we've got multiple things that we're monitoring. And as you can see, there's a bunch of things being called. And we exited after 1 second already, so we didn't even get to see as many things that may be used. libpthread is obviously going to be used significantly within the system, because threading is quite important to most operating systems. So that's why you see quite a high number of usages in 1 second, basically. So that's just showing us now we have the ability to run multiple different probes within one line, but they can each execute different pieces of code per probe. An example of testing the interval probe would just be printing hello world after 1 second. So keep in mind, this is not a frequency. So for example, sorry, and there's no exit attached to this, so it's printing stuff, but it's printing it in the background, and once I hit Control-C, we'll see all that data. If we wanted to, we could do exit here, and there we print out hello world once exactly, and then we exit. You can chain up as many of these as you want to, and we'll get to that in some of the later examples, where as your scripts go bigger, you don't want to have them on one line, but you do want to do different things for the different types of probes that you may be monitoring. Right, so at this point, we aren't going to be depending on this game too much. It was meant for a slightly smaller crowd where we could test this a little bit easier, but there is a client-server setup running at the moment where I have the server running on my, the client rather, running on my machine, and it talks to a server that's running on each of your virtual machines at this point. Now this application exposes two ports. Port 1 is for scoring points, and port 2 shuts down your application. Thereby, and if it's shut down, it can't score any points for you. Now, the idea is we will, over the course of this workshop, work with this example to practice your skills at what you've learned. So, for example, with exercise 1, we need to figure out where the application is running from and what's causing it to run, as well as what's causing it to crash and why it's not running to completion, right? So to do that, your first exercise will be to go log onto the machine, find the application, but as touched on in the previous slide very briefly, don't use your common conventional Linux tools to do this. So use any of the BPFC tools that we've got installed on the machine for you. Write your own BPF trace one-liner, or use any of the BPF trace scripts that are on the machine itself to find out where this application is running from, and then find out what's causing it from running, because it's running but it's not running successfully. It seems to be crashing very often. So we'll give 10 to 20 minutes to do this. I don't know if folks will need the full 20 minutes for this, but I'll check back in 10 minutes and see how it's going. Is there any questions before you get started with it?
Am I allowed to say I'm scared?
No, you should not. You should not be scared. But just know that if you don't find the application in time, it will shut down and delete the VM. So time is of the essence.
Nice.
For folks that don't want to do this or don't have a virtual machine for any reason, I'll show how we go about solving this later. So don't stress if you don't want to play along right now. You can obviously do this on your own time. We'll make all of it available there. We'll make all the examples available later, as well as the slides.
So the purpose here, if I understood correctly, is to you have an application running, and the goal is to find where it's running at, right?
Correct. So you need to find it because, well, it's not in your home folder, for example. So where is it executing from, so that you can run it manually and try and understand what's causing it to crash. But you can't execute it manually until you know where it's currently located. So you'll need to use your tools to locate the binary, locate what's causing it to crash, and if you want to, you can stop it from executing until you debug that.
Okay,
So
thank
yes,
you.
you're spot on. I should mention, obviously, that to be able to find the application and fix it, it is definitely doable using the slides that we've, the scripts that we've executed at this point. I'm just going to go ahead and probably copy and paste them to the command line to the chat if you haven't already found the one-liners file that is on the machine for you. So just in case you're a little bit lazy, I'll paste that for you in chat. Just going to do a 10-minute check here, find out if people still need time, or do we want to continue at this point. And I can sort of show one of the ways that you could have used to solve this problem.
I think we're good if we went for it.
As in continue.
My one vote out of 20.
Sorry, like you're super soft. I can't hear you.
No, I'm saying sure, let's go.
Okay, cool.
I'll just go.
Cool. So I'm just need to exit all my local consoles. So if you haven't figured out at this point, just using the built-in BCC tools, one of the ways, again, there are multiple ways you could have done this. I'm just going to show the simplest way. We would run exec snoop, and if we ran that now, every second we notice that something is sleeping and running, and I guess the name probably gives it away. So we know that this TMP2 challenge binary is doing something, so at least now we know where it is. So if we went into TMP2 challenge binary, we'd see that there's this looper script that's keeping it going, as well as a little config file and the binary itself. At this point, the next question is what's causing it to shut down, and we don't know exactly what there could be, but if we try open snoop, which tells us what files are being looked at, we'll see every second the challenge binary looks for this file called tmp find me, and it's getting it's not getting a file descriptor back, it's getting a -1, which means it couldn't find the file. So all we needed to do at this point was just do a touch tmp find me, and you'll see now the application basically stops coming up in the constant logs. It opens it once, it continues its processing, and now the rest of the system continues. What you may have noticed as well through the open snoop as well as exec snoop at some point is that cron is executing reasonably often, and we probably want to check on that. And if we just have a look at our cron tab, it's probably in the wrong user at this point. So you'll see that the cron is set up to run our script on a minute-by-minute basis, but it only runs one copy of the script, which is where flock comes in. So we just comment that out or delete the line, whatever is more comfortable for you. We could leave that in place. It just means that with that running, we can't really run a single copy of our application because the ports that it binds to won't allow it to run twice. So if we exit that, now we should have only one copy of our application running, and we can continue basically at this point. So this was just one example, like I said, and possibly the simplest example. You could have done the exact same thing using BPF trace, using some of the examples that I pasted in the chat. You would have been able to find the files that were being accessed successfully or unsuccessfully in the temporary folder. You would have found the cron executing as well, and you would have found the challenge binary spinning up for a second, spinning up for less than a second rather, and then exiting. What's interesting to note at this point is that if you didn't use exec snoop or something similar, if you had to just look at PS at any point in time, if you had to look at PS in any point in time until we added the find me file in place, the binary exits so quickly that it would never have shown up in the PS dump that you saw, that you see now. Obviously, it's obviously in place now because the binary is running and everything's happy. But if it wasn't for that, file being in place, you'd never have known that it was the challenge binary that was running every second or less, rather, in the background. Cool. I don't know if anybody needs a break, but I'm going to assume that if you do need a break, you can go now. I think things are going a little bit slower than I expected, so we're a little bit behind on time. I don't want this to run too long. If you feel you need a break, I can pause now. Otherwise, I think we'll continue. I'm going to give it a minute for anybody to shout for me to pause. Otherwise, I'm going to continue. Right, so we've done the basics of BPF trace, and BPF trace is still super important, but we need to get a little bit of a better understanding of things. How do we put together bigger scripts? How do we run things without needing to paste it into one line and hopefully not miss a typo somewhere in there? Let's also look into our function calls a little bit deeper, understand the scripts as I mentioned, and one of the scripts that we've been using up until now, the counting of system calls, is also part of the tools that you have available on your machine. So while we've been using BPF trace for it, the exact same script is available as part of the BPF trace application, and you can see it's actually fairly simple, but they've expanded it, and we'll dig into this expansion a little bit now. I just need to check. Right. So what is the script doing in a bit more detail? Hopefully everything here should be familiar to you, except for the fact that we now have a begin and end. As with most scripting languages, you sometimes need to do something before and after the script runs. And in this case, anything you put in your begin will get executed as soon as the script starts, before any of the trace points are hooked up, and then the end script, the end block rather, gets printed at the end once you hit Control C, for example. Things to note here is also that the author has added two maps. So previously we were doing, because it was all one line, it was a bit harder to do this, but they've now got a special map for syscalls where they're counting the number of syscalls, and they've got a separate map. Just checking. Okay, I can pause for a second while you reconnect if you want.
If you don't speak, it's going to wonder if the sound
Okay, yeah, cool. So as I was saying, that there's two maps now, and that just allows us to collect more data while the script is running. They're both doing effectively the same thing, which is just counting the number of processes. And at the end, unless, compared to what we were doing previously, we're now only printing the top 10. If you remember previously, we used to just print out the entire map, which gets way too much if you think about it when you're trying to find just the noisiest syscalls or just the noisiest processes. So now if we look at the print function, we see that it takes a comma and a second parameter, and that allows you to specify how many you want to get printed. You need to make sure that you clear your syscalls, your maps rather, in your end script, otherwise they kind of get persisted till the next time. As mentioned, because you can communicate across applications using these maps, if you ran the script twice, you'd end up having multiple people writing to the same map, which would obviously throw things off, which you don't want. Now, a lot of this ending bit is handled implicitly for you when you don't specify it in an inline script. So for example, the clearing of your maps, the clearing of name maps are never done automatically, only anonymous maps. Anonymous maps are maps where you don't specify your name, so you just do @ and then whatever value you want to store in there. That's an anonymous map. A named map is one where you have at and then a name after the at sign. So you have to clear those, otherwise they kind of persist forever. So just we're going to run through this very quickly in the console. So you can put this into any file that you want to. I called it by, even though that makes absolutely no difference. And we do sudo eBPF trace and then test.by. And there we go. So it's doing exactly what it mentioned. It'll always, BPF trace will always tell you how many probes it's attached. So in this case, there are multiple that matched our current syscall. Sorry, the three maps are, sorry, the two maps are counted as probes as well. So now it's busy collecting. If we hit Control C, you'll see it's printed just the top 10 syscalls and just the top 10 processes. Now they're obviously not related because we didn't relate them in the map. So this is just the top 10 syscalls by possibly any number of these, any one of these applications. So it could be Chrome that's generating all of these, and the rest are updating only syscall 24 until we don't use the previous example. We don't use the same code as our previous examples, we won't know who was causing that. So that's just an example of a deeper or larger script. And if you look at the BPF trace toolkit, as I mentioned before, or even on your disk, you'll see all the .pt files. And these are simply the same applications that you've been executing in the script form. So it's a great place to go look if you want to understand how a tool is doing something that you would like to do, but you're not sure how. So in this case, they're showing you how to use variables, how to do some arithmetic as well in line, which I don't think we need to cover now, but if you wish and you need to do something like that in your scripts, this is a good example. So again, we're only triggering the interval S1, and then we're getting a kernel address, which if we look here, it gets us a specific address from memory, and then uses that value. That's not something I'm going to go into now. It's just a nice example of reading the average run times to show you how load is calculated on a machine using BPF versus the proc file system. So as we kind of saw in the previous slide, this allows us to set up and tear down a lot easier. We don't have to write multiple scripts to do different parts. You can combine multiple pieces of functionality into one, and you can set up multiple trace points, which we didn't do in our example here, but you could have put another trace point at the end that collected different syscalls and then printed it at the end just as much. But now back to our old friend, the Hello World application that we printed way back at the start of this talk. We're going to dive into this and try and write a Hello World Python BCC toolkit application, whatever you want to call it at this point. So to break this down in a sort of line-by-line fashion, for those of you not familiar with Python, the hash bang at the top just indicates to the Linux environment that we want to invoke this script using Python, and then we import the BCC, the BPF object from the BCC library. Now this library needs to be installed, but in the VMs that we've set up, it's already been installed. Typically, anytime you install the toolkit, the library gets installed as well, because it's used fairly often, as you'll see as part of their standard process. Now, while we are using Python in a lot of these examples, you can also do this in Lua and Go, as well as C. Personally, I just find Lua and Python close enough that it's just easier and more useful to do stuff in Python. But if you find that Lua is a little bit more compact or your style, go ahead. It's just as simple as the Python world in terms of working with BPF applications. Go and C, unfortunately, make things significantly more tricky. Go expects a lot of the code to be compiled ahead of time, and then C is, well, just C, right? Like you need to be super safe about what you're doing. Things get tricky very quickly, and imports are not always where you expect them to be. We've got an example of using C later on in the course, but for now we'd rather not touch that. So this is just showing you how we import the library. So if we look back at our Hello World application, you can see we've got a big string defined, and this makes up the vast majority of the application, right? And what this bit within the prog string is actually what our BPF application is. So in this case, the important bit is we need to get the function definition correct. It always needs to return a integer. You can call it whatever you want to, and then it takes a context. The context we mentioned briefly at the start of the talk as well depends on what you're hooking into. So for example, on the network stack, you'll get access to packets, but with syscalls, you may get access just to the syscall ID. We're not using it at this moment, so we leave it as void. This text within the prog variable is C, but it's also not exactly C. A lot of it gets interpreted by the BCC toolkit and either expanded or reduced a little bit. But we'll get into that a little bit more later. So for now, just know that this is how you define a method in terms of actual BPF code. This is what will get translated into BPF assembly and then get injected into the kernel. So in our case, we simply printing out the word hello world and we're returning 0. You have to have a return value for your function to work as BPF, and the kernel uses that often to make determinations whether things are running successfully or not. The BPF trace print K function is one of the functions that we talked about. Don't have it here, BPF. In this bpf.h file, if I copy this quickly, it's one of the functions that you can use. Like I mentioned, there aren't a lot of them, but this is the format. This is an example. This gives you probably the most up-to-date and correct information in terms of using the BPF print, trace print K function. For our purposes, we're using it as a console.log or a print output, but keep in mind that it's not the best way to be doing debugging and printing. The reason for that is all BPF applications, so if you had a number of function calls here and you loaded these applications into memory, all of them write to one log file. This log file here at the bottom, syskernel debug tracing trace pipe, and you don't want to have a case where things are printing to the debug file out of order, and you have race conditions and you have different applications writing in different orders. So in our simple example it works, but once we get to a little bit more advanced applications, or you have multiple applications running, there's better ways to do this. Now, once we've got our string set up and stored, we obviously need to compile this code, and BPF, the BCC toolkit takes care of that using the BPF object. You provide in either text with a raw variable, as you see on line 1, or you can pass in a file name and it will read the contents for you. Then the most important bit actually happens. So similar to how we did with BPF trace, you need to attach your BPF code to a probe. If you don't attach it to a probe, it will never execute. So if we just took out line number 2 here and we ran the application, nothing would ever happen. The code would get compiled, but it would never get executed, and things would never work the way we wanted it to work, right? There are 2 bits to understand from this attached K probe. You typically always attach to a K probe, even though you may use a user probe here. The event is the kernel probe that we would have seen if you did BPF trace -L. So any one of these probes is what you would add for the event, and then the FN name or function name, hello, is what we defined originally in our function name within the prod variable. So if that doesn't match, again, the code won't execute, so make sure that you get the correct names in place. And then finally, we hook into the trace print. This simply reads the log file that we talked about earlier and prints it out to your console so that you don't have to tail multiple files and look at different locations at the same time. Something to note though is this attach kprobe is not the only format. You can attach a kprobe without needing to specify the event. As you can see, it's an optional parameter, so you don't need to specify the event here or the function name. Instead, we would have created our function name in the format shown here. So it would be kprobe double underscore and then the kprobe name, as well as all the parameters for that function. What BCC does in the back end is once you run the application, it says, oh right, you've used this naming definition kprobe double underscore, right, go turn that into a kprobe and attach it and attach the code to that kprobe, and you don't need to care about a function name at that point because it's all being compiled to bytecode. So that's the other way to do it, but personally I find the attach kprobe method here a little bit easier, since you can then create multiple functions and change them around a little bit simpler, if I can put it that way. So with all that said and done, there's a lot that you can't do when it comes to BPF code, and specifically the BCC toolkit in conjunction with either Python, Go, or any one of them. You can't use loops, you can't do function calls, you can't do any sort of undefined behavior. Everything must be checked before you access it, and I'll explain what that means shortly. And you can't access random bits of memory aside from what's available in your context. So when I say no loops, that actually means no loops, no for loops, no while loops. If you do want to use a while loop, there is a functional way of doing that. If you want to use a for loop, the BCC toolkit provides you a helper function that will unroll the for loop for you automatically, so that it results in non-looped code. You can't use function calls, and when I say that, I don't mean that you can't call something like BPF trace print k. I mean you can't create another hello function here, call it hello2, write some BPF trace code in here, and then just call it from your original code. So if I try to do hello2 here, this would actually fail. There's no way to do that. So you can't separate your code into multiple functions. Everything needs to just be in one large function. The way around this, if you do want to do it, is again to use another BCC helper called inline. So if you specify inline, the BCC toolkit, when you compile and run the application, will take whatever you've put in this function and inline it in place of the function call, so that it seems as if you're calling a function, but everything is just one big function in the end. It's part of the limitations of the BCC toolkit, so that you have no what you call it, undefined behavior, and everything is constant time. It's an easy way to say that this function will definitely exit, and we can say that because we know it's not calling anything else. Let's get back to this. So like I mentioned, no undefined behavior, so you can't just go and access a pointer directly. You need to check that the pointer is not null first or not zero before you access it. If you do want to do function calls or looping, you can sort of do it using what's called tail call execution, which means at the end of your function you can effectively call the function again, but we're not going to be covering that in this talk, because honestly it's it's just a cause of way too many problems in terms of following the behavior of the application. And then, like I said, no random access memory, so you can't store anything in your function. The only way to store data between calls is to use a map. As mentioned, if you want to do anything, you pretty much have to rely on BCC to go and unload loops, inline functions, and basically make your life actually semi-usable. A lot of that is described in the reference guide. In the reference guide on the repository. Okay, I guess it's not in this document. There is a document that they have which covers how to do all of this. Right. So before we go ahead and do that, I just want to go and run this application so you can see what it looks like from the console. You can run this on your own as well. I'm just going to paste it in the chat. I don't know how to format that as code, but I guess that sort of looks reasonable. Now there is a bug in this application, and I'm almost hesitant to run it before I let you figure that out, but I'm going to go ahead and run this anyway. So while you possibly run it on your own machine, you may encounter a bug, and we can talk about that if you want. Otherwise, you can just copy and paste my example. So I've just pasted my code here, and I'm going to do Python 3 test.py. Please make sure on your VMs as well that you use Python 3. The Python 2 version doesn't have the library installed. So as you've seen probably before, you need sudo to run any of the BPF stuff, any of the BPF programs, because it can't make the system call for the BPF syscall without elevated privileges. So I'm just going to rerun that again, and this is going to fail. Now, the reason why I let this fail on purpose is because, as I mentioned before, you can't run a BPF application unless it's attached to a probe. And as you can see in the error, it says here, cannot attach kprobe, probe may not exist. But surely the sysclone probe exists, because otherwise many Unix things would be failing if we didn't have the clone syscall in place. So to work around it, we probably need to understand what's happening here. If we do a search for sudo bpf trace-l and we specify sys_clone, you'll see that the kernel probe definition for sysclone on this machine, and probably your Ubuntu machines as well, is slightly different. So it's not just sys_clone, it's x64 or i32 sysclone, and those are the probes you need to be attaching to, not directly to sysclone. So if we copy that, edit our test.py file again, change the event now, put in the correct name. Remember, you don't need to specify the full trace point here. It's assuming that you're attaching to a kprobe, so you only need everything after the colon. And if we are, and we run that again, give it a second, there we go. And as soon as something runs the clone syscall, you'll see it will print out a new hello world. So if I do ls, if I type, something is running the clone syscall, and it generates a hello world print for us. So that's the equivalent of a BPF application now running in kernel space, hooked to the sysclone function, a sysclone probe, and executing the print k hello world whenever we do something with that probe. Now you can attach that to whatever you want to, and once we hit Control C, that code is removed from the kernel and is not executed at all. To prove this for you, I'm going to do a cat on, I need to find the file name again. So if we look at this, so remember everyone in the system is writing to the same file. So if I cat this out, you need to use cat instead of tail for some reason. I can't remember the difference. but it's the same output. We run the script again, open a new thing, and you can see it prints to both of them. Okay, I guess that's why we use tail and not cat. Ubuntu seems to like cat a lot more. Let's just type more here. Yeah, for some reason tail never seems to work for me, even though the docs often tell you to use. So there you can see it's printing every time in both consoles. I guess you can't see, but it's in sync. There's 178290 and we had 178290 from our cat as well. If we now stop the application and I continue typing or opening new terminals, you'll see the log file doesn't grow at all, which indicates that the application has been loaded out of kernel space and things are continuing as normal and there's no more logging being done. Now you shouldn't ideally be using this, like I mentioned, because any number of BPF applications are probably writing to this file. Just because you don't see any output now doesn't mean it doesn't exist. We'll cover how to handle that a little bit later though. Is there any questions around this Hello World application that is not clear, or anything that you would like explained a little bit further before we go on? Going to assume that everybody's having a great time and that there's no issues with their code, and we're going to continue now on to maps. So we would like to be able to control our BPF applications from user space, but as you saw in this sample code, we simply attach to kprobes. There's no way to say run this function now or function X later. It's always running one function at any one point in time. So how we do that is we work around that limitation by using maps that are accessible between the user space and the kernel space, and setting values within the maps. So as mentioned previously, maps are just simply hash tables or dictionaries depending on what language you've used it before. But basically they're just a key value structure where you set a key and a associated value with it. You can then look it up extremely fast because it's always a constant time to look up that value. So why does this work? Because we're not actually talking directly to the kernel space. The kernel space and user space are just looking at the same location on disk, which is a virtual file system that maps are stored on. So when both a user space application as well as a kernel space application try to read a map, they're just looking at this virtual file which has the data stored in it. You could look at the files yourself. We're not going to go into that right now. It's all in binary data, so there isn't really much benefit in trying to look at those files, even for debugging purposes really. So how would you toggle printing in our Hello World application? For example, this is some pseudocode and it's not exactly how you would go about doing it using eBPF and Python, but I've just split them into two parts. So this is the equivalent of our hello function, and then the bottom bit is the equivalent of our Python code. So what you would do in the BPF code is you would look up a map and a key. First you'd need to define the map, obviously. Then you look up a value from that map. You check if the map is not equal to null, and if the map value matches some value that you are interested in, then you would print. So in this case, we're just checking if the map value is not null, because obviously we can't deal with undefined information, and the value is equal to 1, then we're going to print the word hello. And then on the Python side, how you actually set that map to either 0 or 1 can be entirely up to you. So it could just be in a while loop that you read from a file. It could be more complex than that with a Flask application that gets a value from a post request and sets this map, which then updates the BPF application and starts printing at that point in time. So this is just a high level example of how you would go about doing that, and it's how you can control your BPF application. So while we're just doing printing now, you may want to, for example, disable or enable a rule in your network filter based on a value that the user space is sending. So if the user says, I want to block all incoming packets that are meant for port 443, you could set the key value of port to match the port number, and if that port number is looked up for this packet, then we block it. Otherwise, we just continue allowing packets. So it's not a direct call, it's more a indirect method of controlling what the BPF code does from user space. Now, the BPF application as well can send data to user space in the same manner. So instead of just looking up a value from the map, we swap this around. So you would say map sum key is equal to value. Obviously the rest of the code doesn't make sense here, but that would allow you to set some value from the BPF side, which you could read in your Python code. So for example, if we were collecting the number of packets, we could collect that from the BPF side and just pass it to our Python code and have that printed out. Now, if you think back to the original code the original example that I showed with Brendan Craig using his mobile device Wi-Fi connection as a theremin that played music, that example actually works fairly well now. So if we just do BPF there we go. If we look at his source code now, it's actually fairly understandable. So let me just zoom in to this a lot. Okay, and we zoomed in too much. So I hope everybody can see this now. Okay, I guess you can't see that. I'm just going to paste this in the text channel as well if you want to read this on your own. So effectively explaining how he determined his Wi-Fi signal is here in BPF trace, and he found a K probe for his Intel wireless LAN card that had a debug function that was printing an argument of argument 4 that had the RSI, which is the signal strength. And he simply printed that using the printf function, which got printed to the console, and that's how he did the initial exploration. Once he understood how the strength was being printed, he then expanded this a bit into a more fully featured example, which is what you saw in the demo, and he used Pygame. So he sets up, let me highlight it. So he sets up his BPF application using the K-probe format here. So this is the alternative method that I mentioned before. He's setting up a K-probe for that Intel wireless LAN debug K-probe. He has to specify all the function parameters, and then he just prints it out, extracting the value he wants. Then in a infinite while loop, he extracts the value using the trace fields function, which is the same as the trace print function that we had, except that it splits it into a not an array, it's a list of Python values, and then you can look up the task PID, and then the message is the last value. And since he's been doing that with printf effectively, he's controlled how the values are being output. So he splits the kernel message by space, which gives him his value, which is his strength, and then the format. Then he checks if it's got the correct format, and then using Pygame after that, he makes a sound depending on the signal strength that he's gotten back and keeps the loop going on forever. All of this is showing how you pass data. It's not the only way, and it's definitely not the way to do it using maps. It's just one of the ways that you can pass data from the kernel to a user space application, pass that data out, store it, save it, process it, and then act on it. So all this stuff at the top is not really useful for us. It's simply setting up Pygame parameters. This is the actual core of the application, which gives us a fairly nice example in terms of showing a demo that talks between user space, kernel space, and gets everything working together. So a few more examples that we'll probably go through depending on whether folks want to or not. I'm not going to specifically dig into the per CPU map, but just to explain on a high level what that does. So right now we've talked about maps that assign a value based on a key, but what happens when your code is now being executed by the scheduler in the kernel on multiple CPUs at one point in time? You have conflicts, you have race conditions, and then you need to start locking your code, and you need to start building way more complex applications than you really wanted to in the start. So BPF works around this by providing what's called a per CPU map. So effectively, you define it once as a map that would work on an individual CPU. In the background, it's spanned across each of your CPU cores, and then the data is collected and presented as if you had run it correctly across multiple cores without you needing to do any of the maths involved with that. So I'm not going to walk through this example because it actually gets quite involved, but you can see this is the part that we care about, where we get the table, which is actually just the map. So they call it in the underlying code tables, and then we loop over each of our CPUs, initialize them, and then update them later. It's not something you should need to care about right now, but if you ever do any CPU profiling, that's the one time where you'll definitely encounter your code being executed on multiple CPUs at the same time, and you'll need to use a map that spans multiple CPUs. Now there is a number of other maps available, but we're definitely not going to go through all of them. The simple key value map is more than enough. There's an array map, which works very similar to an array, but also a map, and each of these has different use cases. Just want to find BPF maps. If you just Google for BPF maps, you should find it on the in the kernel documentation. Fundamentally, they're just wrappers around wrappers around wrappers. So you can see. Okay, I can't seem to find it on this example here, but there is good documentation explaining the different types of maps. But this is just showing you how you would interact with it from the BPF side. I can't find it now. But there are different maps if you find that you're encountering issues with the default map type. Now another example of using maps is in DDoS detection. So you want to keep track of information coming from the kernel, but also send that information to the user space. And I just want to check that we've got an exercise after this. Yes, we do. So we've got two options at this point. The exercise is fairly simple because unfortunately I didn't want everybody to go and write out map code on their own. So it's more for filling the template. So if you want to, there's two things you need to do from this class. The first one is fairly simple. The application that you are running at the moment on your servers is receiving data, or at least if they're up and running, and accepting connections, it should be receiving data from a central server, and that server is passing a list of IP addresses to you. This was originally meant to be a way for you to find out who else was on the network, so that you could fire back at them and shut down the applications. But for now, because that unfortunately gets a little bit too complicated, you just need to trace out a internal function within that binary that will leak out the IP addresses once you find it. After that, in the courses folder, there's a script called app.py in the map exercise folder, showing how data is passed back and forth between the user space and kernel space. Your job is to go and get it to print the word dynamic communication. Now keep in mind, because of the way it's set up at the moment, it's not using the trace print function. You can add that if you want. Alternatively, it's easy enough to cat the log file, which I can print in the chat room if needed, so that you can see that it's being printed out directly. The alternative is, if you really want to go and do some advanced communications, is using the correct way to do messaging with an eBPF. And I'll run through this article if folks get through the first two bits of this example, or I don't know, Leon, if you think we should discuss the DDoS and the correct way of messaging first, and then let people go try the exercises. Okay, so let's do this. Let's just go through a quick example of what's the alternative way to show maps being used. And this is how you do messaging from the kernel to user space using maps instead of the print K statement that we've been using up until now. There isn't a great example of this, and this article is actually one of the better ones. So we create our BPF application as we have done before, and we attach a probe for test purposes, just like we did with our Hello World application. As you can see from the example, it's really quite simple. It really does nothing. It's just doing a print like our Hello World, except it's using the wrong method. So the correct way to do it is to use what's known as perf events. Let's scroll down a little bit here. Alright, so we need to define what's called a BPF perf output. This is just a wrapper for a map that's used internally, but it allows you to keep track of things a little bit easier by allowing you to specify a custom data structure that you want to send later. So in this case, we define so the custom event here is the name of the map that we're creating, and its type is a perf output. This is our BPF code. So we create a structure of OMG data. We store within that data, within that struct, the current GID, the current PID, and then the group ID for the user as well. We then get the current timestamp in nanoseconds, as they clearly point out here, and store that in the structure as well. We get the application name using the BPF get current com function, which reads from our context. So this is the first time you've probably seen context being used aside from networking. So we get the proc name out of the context, and then we use the custom event.perf submit. And what this does is it effectively triggers a event on our user space side. So if we scroll down a bit, you'll see they've created a function called print event, and we attach the event, the function that we want to call whenever this event is triggered, to the map custom event. And open perf buffer is how you do the attachment. So effectively, anytime this is called, this print statement will run, and you get now a you can read out that custom event data and do whatever you want with it. So in this case, all they're showing is that they traced the sysclone event using perf messages instead of using the print k example. This is the only way you can ensure that your applications are not sending conflicting messages between each other, and it allows you to have multiple applications listen for the same event. So for example, if you've written an application that traces network events in a unique way, instead of requiring somebody else to go and write the code all over again, they could just load your application into the kernel and watch that same map that you push data out to, as an example. So this is the correct way to do messaging between kernel and user space, but as you can see, it's significantly longer than just calling traceprint. And then our DDoS example. So the DDoS example is it's not fully featured in that it won't go ahead and block anything. It's simply detecting an increase in packets and then alerting the user. Let me just see if I can print this out to raw so that it's a bit larger so you can view it. Right. So as previously shown, we do our basic imports. The only difference is we now need to start using C types because the data that's being passed between the kernel and user space needs to be the same types, and that happens to be C types at this point. We define our hash for storing the received packets. They have some defines to make life a little bit easier. We then create a packet for messaging, and we create a perf output that the user space will monitor. The detect DDoS function is hooked up at the bottom here onto the IP received. This is using the same method that I showed previously, where we attach a kprobe by event name and function name so that you don't need to use the predefined format. All this function does is initialize all the values it's ever going to use for lookups. So in this case, it's using a receive packet index set to 0 and a receive and a transmission and a elapsed time index set to 1. I'm not going to explain all the text here. You can look this up if you want on your own. But effectively, we then use those indexes that we defined earlier to look up a value from our map. The maps were defined earlier. We then go and we have to check that they're not null. So in this case, we check that they're not 0, and then we do a simple time diff. If it's less than the timestamp that they defined earlier, which means basically someone is sending packets too fast, we increment the value in the map. As you can see, this is a pointer that was defined earlier. It was defined there. So we increment that. We check if it's greater than the amount of packets that we care about, and then finally we update our map. Once the map is updated, we've got a monitor set up on the user space that will check for that packet, and if it sees an increase, it will just print out DDoS attack and the number of packets that you've received at that point. Now, once we get into the next section, which is XDP, you'll see how we can possibly, they don't have a great example of this, but how once a event is triggered, we could block packets that are coming to a specific port based on a specific IP. And that's just a simple example of how you could use DDoS detection. Well, it's not really DDoS detection, it's just denial of service detection based on a very simple algorithm that says, is the number of packets coming in too fast? And that's just one of the examples I think that are worth looking at. So like I mentioned, If you can find out what the IP addresses are, I'll give 10 minutes for this. It's really quite simple and very much similar to what was done in the first exercise, slightly different, and then go ahead and complete the map exercise code. Once it's done, we can continue with the next section. As always, feel free to ask questions if things are unclear or things are not working on your side. So I just realized, sorry, while double checking things, there may be a issue with the path that the challenge binary is running from. So you may need to kill the binary with a kill -9 or something, and then manually start it from the TMP2 folder if you're not seeing any results in terms of IPs coming out of the application. Um, so I'm going to make a call rather, and just double check that everything is okay. Otherwise, I'm going to try to solve this very shortly. Give it another 2 or 3 minutes just to make sure I can actually solve it, and then continue. Right, let's finish the section off very quickly. So I'm not going to demo how to solve the BPF map. It should be fairly simple if folks are interested. If we have a look at the course folder, and then exercise, and then all you needed to do here was set the control value. It was just set to fuzzy here, which was obviously invalid. You just needed to set it to 99 and ensure that the control hash was being set correctly, and then on the next loop it would have triggered that and it would have worked correctly. You would have only obviously seen that get printed on the debug file directly, since we don't have a print statement set up in this code. So that was a fairly simple one, but again, getting people to type out all that boilerplate code is quite a bit of work for nothing. So on to tracing the actual binary. As I mentioned, the folder needed to be set up correctly, otherwise it doesn't find the port mapping. I think so, at least that's what I seem to have experienced. So now it's running at the moment, and then in another terminal we need to find out now what functions are executing in the binary. And to do that, I ran the fun count on my binary, and if you leave that running for a second, just wait for a new connection, which happens every 20 seconds. Let's just speed that up. I see somebody else managed to get this working as well. If we hit stop at this point, you'll see that the three main functions that were running internally within my binary was do something, send and receive. So send and receive definitely relates to the fact that this was now networking related, and do something, while we don't know what it is, it definitely seems interesting. So to dig into that a little bit further, I used our friend BPF trace, and I set up a user probe trace on the do something function, and I did a printf on the first argument that was sent to the function. Now, while I didn't look at a full detail dump of what the parameters were, I took a guess sort of that there was at least one, since something was happening. The only difference here was you would have needed to figure out that you needed to use sarg0 instead of arg0. If we look at, it's not listed here, it's on the reference guide. If we look at sarg0, the difference between arg0 and sarg is one is a stack argument and one is a function argument. So in our case, Go uses stack arguments. So if we ran that, wait for the connection to execute a few times, or I can just forcibly run it again, and we hit Control C, you'll see I didn't do printf nicely with multiple lines, but you can see I was sending the IPs localhost 127.0.0.1 and localhost 127.0.0.2. And if we just make that a little bit prettier, let's put a comma, backslash n, or semicolon, and we run that again. Just rerun our function, and because I've got the new line in place now, it actually prints it live. So there you can see, as the connections come through, you'll see it coincides with a added new connection. it'll print out the list of IPs that were being sent. And that's how you would trace data internal to an application when you don't have access to the source code. For example, you could run this against a PID if you didn't want to use a binary directly. So if you weren't sure what the startup arguments were, for example, to rerun it again, BPF trace allows you to send to specify a PID that you can attach to while running. It's obviously useful in production where you don't want to interfere with applications, but you still want to debug what's happening within those applications. As a matter of interest, I just want to check what user probes the application lists. So as you can see, if you did this, you would have found that we already had the main.do something there. We already had main.star. The main comes from a Golang function call, so that's why everything is prepended with main. You could have like monitored any of the other Golang functions directly on your own. We just chose not to do that for this example. So that sort of covers monitoring the internals of an application live. As you can see, we found network data as it was being passed around, as well as communicating with maps between user space and the kernel. So onto the last section, and hopefully the most interesting, but probably the shortest as well at this point, because it's where things get really technical, unfortunately, is network programming with BPF. When we talk about network programming with BPF, we're talking specifically about XDP. XDP stands for Express Data Path. Why you would want to use this is because it is excessively fast, very efficient, and allows you to do the dynamic program control that we've just shown previously using maps. So why is it so fast? It's so fast because it's specifically executed before packets are even processed within the kernel's networking stack. So you get effectively direct memory access to packets, and this allows you to filter and modify packets extremely fast and extremely efficiently, so you don't need to spend a lot of time allocating memory to those packets before they pass to user space or other parts of the kernel. Now, this is achieved via one of three driver types which XDP uses. The order you most likely to use it is generic, native, or hardware offload. Generic is just a catch-all driver that you can use on any machine. It's unfortunately also the least efficient of all the drivers. It's basically as slow as processing the packets in user space. It does this because BPF has to effectively fake a native driver, and it's obviously bypassing the drivers that should be doing a lot of this processing for you. So we're losing a lot of the benefits of XDP. Native and hardware offload is where things get interesting. Unfortunately, you need a fairly expensive network card, or you need to use the enhanced network drivers on AWS to be able to get access to this. But this allows you to, again, as mentioned previously, process packets before they hit the kernel or user space and before they hit the normal networking stack within the kernel. So you can effectively bypass IP tables when you process using a native driver. Hardware offload is the most rare at the moment. As mentioned at the bottom here, only Netronome cards support it at the moment, and this is the peak level of efficiency. Your BPF or XTP programs rather get run on the network card itself, so you're not even using any CPU processing or CPU memory at that point to process the packets. You're filtering it before it even gets into the kernel itself. excessively fast, and the benchmarks on this are really amazing. Unfortunately, most of us are not going to have access to this. Intel and Mellanox, I've never heard of Mellanox before, but Intel is still in the process of building their drivers. But again, you're looking at your 10 gig network cards that are only likely to process this. So desktop and generic servers are unlikely to have access to this level of processing just yet. So unfortunately with XTP, it's also one of the bits now where we need to start diving a little bit deeper, and you need to attach this code to a network adapter. You do this first by compiling the code to a object file, and then attaching it to an adapter. Please, because it would mean a lot of wasted time, don't attach this to the ETH0 of your AWS instance. The example code that we'll be showing now blocks all traffic. So the last thing you want to do is just lock yourself out of your machine. The only way to get access is to use a serial console, which we're not going to do at this point. We'll probably just destroy the VM at that point. You will also need to understand some of the packet-specific code that the kernel does. So how do you pass a IP header? How do you pass a Ethernet packet? But we have provided templated code around that, so you don't need to worry about that. So for now, use the templated code, and then if you get some time later, go read up on the structures that the kernel uses so that you can pass the packets without having to write all the passing code yourself. So as mentioned, we're going to write just enough C to get the point across. Don't be scared when you see the next few slides. So there's no Python code involved here. This is all C, unfortunately, and it's slightly different to the C you've seen previously. So we include the Linux BPF header at the start. This allows us to access the enums as well as the context structs, as well as a few other simple helper functions that we mentioned previously, along the lines of setting maps, for example. Sorry, 1 second. Right. So we already covered the include, which is just our standard BPF include. We need to define the section headers because you are allowed to compile multiple C BPF applications within a single object file. And to do that, and because you can load one section at a time, you need to define this macro which allows you to set up, as in the case here, a section for your code. So previously with the hello world examples, we would tell Python, oh, I wanted to load XTP prod simple. You don't do that when you're working with LLVM in C. You simply specify a section, and the section is loaded in its entirety. Yeah, so this is simply a function macro that helps set up things for later. Very similar, and the function header is very similar to what we saw with our hello world. Within the actual application now, our return function now actually is way more important. Previously we just returned a 0 for everything because everything was successful. Now our return value is actually what we want to do with this packet that we're processing. Since this simple example does absolutely no checks, and it returns the XTP drop function, it's basically going to drop every single packet that hits this network card, this interface rather. There are other return codes. There's XTP aborted, XTP pass, and XTP TX. Aborted is fairly similar to drop, except it's used to indicate an error code as well, but don't use that unless you really need to. Pass is obviously allowing the packet to continue wherever it was going. TX is allowing you to reroute a packet if you modify, for example, the port or the IP address. You can then pass it on, in the case of a load balancer, to another machine somewhere else within your network. Yeah, so as we covered already, aborted will have the same effect as drop, so it will drop all packets, so don't use it unless you really need to. TX is used for modifying, is used when you've modified a packet and you want to send it somewhere else. Keep in mind though that when you modify packets with XTP, it puts it back onto the network card again and it will be reprocessed. So for example, if you change the IP, the destination port, it goes out to the network card and then gets processed again as if it was a new packet. So to load our programs is slightly different this time compared to what we did with the Python code. First of all, you need to compile the C code that we just saw in our Hello World example. If you look at the home folder now, there is a XTP folder in your courses folder. XTP. If you get the XTP sample, you'll see it's exactly the same as what we demonstrated earlier. One thing I forgot to mention is you have to explicitly define a license for your code. XTP, in terms of the verifier, requires that the license matches your kernel's license. So in this case, the Ubuntu kernel is GPL, so you need to match GPL. If we change that, it would refuse to load the application, and if you didn't provide it, it would refuse as well. Now, to save everybody time, there's already a make file that does all the compiling, so you don't have to type this out and make a typo. You can simply type make all. That compiles our application. Now, typically, you don't need to specify the include path, but on Ubuntu, for whatever reason, the include paths are slightly different, so you have to include it. And then our target is BPF. If you now do object dump on the XTP example.o, I cannot remember this now. Okay, I'm not going to dump this now, but if you looked at the section headers for the object file, you'd see that we had the prog example, the prog section, as well as any other sections that we would have defined in the single binary. Then to load the application, we need to use the IP root application that comes with Ubuntu. So in this case, you would run sudo ip-link set device hello, which is your loopback, and then we have to use the XTP generic driver in this case, and then we specify object and our object that we want to load. In the example that you would load on your machine, it would be called XTP example.o. Again, you can use the make file to do that, but in this example with block all, it's just what we compiled out of the previous step. Once you did that, the XTP application is loaded, and you'll get a small indicator. If you typed IP link to list all the links, it would show you that an XTP application is loaded, and I will demo that for you in a second. But the next most important thing is to turn it off. You can't turn off individual applications. You simply turn off all applications on a link. So in this case, we set hello XTP generic off, which turns off all XTP programs on the hello link. Now, so we've compiled our code already at this point. So if we just check the make file again, we can run make install, sudo make install, and it's given us a bunch of information that we don't really need to care about too much, but it's just telling us there's some debug data that was rejected. So BTF is something that's not very well defined at the moment, but it stands for it's the type definitions for debugging, but unfortunately, because it's so undefined at the moment, it's basically an opt-in thing. You need to enable it in the kernel, and that's not always the case. There was an article posted, I think today or yesterday, where they've now made a lot more progress on it, but there isn't enough information to debug, to demonstrate this in a clear way. So for now, you can ignore that. But you can see the BPF verifier is giving us a lot more information now. It's just telling us where it's loaded, any flags it's loaded, how long it is, and then the data within the XDP application. You can see the function name, and that's really all that you want to get out from this definition. Sorry, one other thing is the type ID, which you'll see now if I do IP link. You'll see we've got a XDP application loaded at the bottom now, which we previously didn't have loaded. I thought that this matches up. I guess it doesn't give it to you ahead of time. So the ID is how you can inspect an application that's loaded. I don't know if the tool is loaded. BPF tool. Sorry, I'm just trying to remember how to do this very quickly. So if you do BPF tool prog loaded 64. Okay, so that BPF tool prog will just show us all the BPF applications that are currently loaded. Ours is one of these, which I cannot seem to see for the life of me. It's probably this one here. And if we wanted, we should be able to view that. I'm just not 100% sure on it is X-lated. Okay, so you can usually dump out the actual raw assembly for a file once it's compiled using the prog command. I'm just having a bad day with the syntax. But as mentioned, you can see that it's loaded, and if we run sudo make uninstall, I don't need to sudo R. So one thing I should mention, if you do try this here, make sure you root before running the install and uninstall. Because we've now blocked all packets on localhost, sudo tries to do a DNS lookup using localhost because that's where the DNS resolver is installed on Ubuntu. But because we're blocking all packets, it can't do a DNS lookup. So as you can see, it hangs nicely, which will resolve itself after a while, but it takes a while before it times out. So if we just go back here, so if you just do make uninstall, since I'm root anyway, and I typoed that as well. Awesome. It's uinstall. If we now go check IP link, you'll see we've got no XDP application loaded, and this will probably resolve as well now. To test this, to show you that this is actually blocking packets, we're going to do a very simple example using netcat. So in this window, I'm going to do nc-lk127.1. That's just a high enough port that it's not going to be an issue, and that's what I've been practicing with a lot. And then if we split to another window and we do nc-l127.0.0.1 7.9, well, we don't want to listen, we want to connect. And now anything we type obviously is going to be mirrored on the other side. So if we go back to our terminal, we do make install, check that our application is loaded. It is loaded. Go back to the previous window, and now anything I type, as you can see, is not being communicated to the previous listener because the XDP packets on that link are now being dropped. Because we're connecting using TCP, as soon as I drop this firewall rule, you'll see it will continue happily retransmitting those packets. I guess not. I guess we probably waited too long. Oh, there we go. So it took a while, but it ended up retrying them, and our packets are being sent again. So that's basically showing you a very simple example of the firewall. The course example that we've got running will show you how to do port checking, as well as I was hoping to cover IP checking, but that's a little bit out of the question for this example. So the exercise you've got left now is to modify the firewall that's running to block all calls to port 1244. That was the port number that was listed under the OPT, TMP2. You needed to block access to port 12344. So you need to modify the code in the exercises folder such that it blocks that. So if you go into block incoming, so this is also showing you a alternative way to run the code. Because we're doing it via BCC again, you don't need the license, but you could have compiled this once you edit the section so that you run it directly on the link. This is an example now showing how to filter by protocol by breaking out the packet. Your job is to fill in the code here such that it filters out it only blocks port 123, and I forgot already, 12344, and you need to block that, otherwise everything gets passed and allowed in on the network. To run it, you just need to run filter.py, which again loads all the contents from there, attaches it to Elo. You need to change this to your current device. I put Elo because I didn't want people to block themselves by mistake. So just make sure your code compiles on Elo. Test it using the netcat example, and then run it on the ETH0 link, and then you can let me know that it's running, and I'll do a test from my side and check that we actually can't shut you down. Cool. I'll check back in 10 minutes if folks are still around. Otherwise, feel free to ping me with questions or get back to me later. Sorry, I'm going hoarse. Sorry, so there's about 10 to 20 minutes for the for the course. That's about it. Yeah, there's testing. Okay, just to wrap this up very quickly, I'm just going to show you the code that would have been needed to change. So if you edit block.c, all you would have needed to access is simply adding the following, which I can't get now. There we go. So what we are doing here is we check if the TCP structure that we have, its destination field, which contains the destination port, we check if it equals to the number 12344. I'm just printing out for debugging purposes, but if it is, we simply return XTP drop. Otherwise everything falls through and we return pass, and this way you can block only port 12344 and the rest continues. Just as a matter of interest, you can also do the following. If we, for example, match port 12344, we can do TCP dash destination is equal to and change that to a 5. And if we now return TX, locally what this will do is it will change the destination port from port 12344 to port 12345, and the packet will now hit whatever is running on that port. And a nice example, well, I'm not going to go do the full example now, but if you ran our netcat example, but listening on port 7999 and then another copy listening on port 7888, you could redirect the port here and you'd see the contents flowing to a different terminal instead of the flowing to the terminal with 7888 instead of the one with 7999 is an example. Unfortunately, changing the direction of ports to a different IP address is slightly more complicated, since you need to ensure that the packet is valid and you recalculate the checksum, for example, and that's a little bit beyond the scope of this and requires a fair amount of checksum manipulation, which is painful to say the least in terms of C code. So I didn't want to get people bogged down with that too much. So this is just a simple example blocking on one port. Obviously it looks more complicated, but just keep in mind that we could have wrapped this whole thing at this point here with a map check and enable it or disable it dynamically from the user space with a Python program or whatever else you wanted to, or even dynamically using a running servers in the background, for example. And with that, I think that's the last slide we have. Actually, the last slide is just looking forward. So some things that we didn't touch on is BPF filter, which is very similar to XTP but based in the BPF world. It's literally in alpha phase at this point, so it wasn't worth discussing. Landlock, which is again very alpha, uses BPF to control file system resources. So you could allow or disallow or even track resources on a kernel level. SecComp allows you to control access to syscalls, but unfortunately it uses classic BPF, which is a nightmare to program with. So it wasn't a great example, which is why we skipped over it for the demo purposes. But if you want to, feel free to read up on that, as it may help you with problems you have. Explore some of the BCC examples. They're great examples to base your new code off, and they're well thought out and well documented as well. As I mentioned, redirecting packets to different hosts is great, but it's slightly more complicated. And then lastly, more from a security fuzzing perspective, is there's a great article on using GPUs to fuzz the BPF verifier, and how that can scale significantly faster than using your CPU to fuzz that. since everything that's in the verifier is effectively just doing CPU and memory only checks. There's nothing that needs to hit the disk, and you can scale that very easily. As always, I'm around either on MetaMost or Teams or even email. If you have questions, please feel free to send them on to me. I'll be sharing the slides in the channel shortly after this. I think that's it from my side. Unless there's any other questions, I think I'm going to call it a day. It's been going on for a while. Thank you for all that attended. Really appreciate it spending, I don't know, like close on 2.5 hours with me. I hope I didn't bore you too much. And with that, I'm going to stop the recording and screen sharing.